participants. So today I'm going to talk a little bit more about the struggles and the process of the multi-environmental trial analysis. I'm going to work a little bit more with the focus on forestry because that's where I have a bit more experience. But here and there, I'll give you a few things associated with probably perennials and some of the agricultural crops. And also some of these things also apply to other things like aquaculture and so on. It's mostly words. I have a little bit of an example where I analyze a trial and study with a couple of trials with its own complexities and its own things. But again, it's not the actual more operational data. It's almost like a textbook's data set. But obviously, many of the things that I'm going to mention apply for more operational things. So, and that's what I wanted to bring these things. And again, if you have like questions or things, you can put them on the chat, and we'll try our best to answer your questions. So one of the things that has come a lot of times is from using multi-environmental trial data is usually for agriculture, we try to select the best varieties, which usually the best clones or recombinant bred lines or whatever. In forestry also, we're trying to select the best clones. But of the other part of it is to do an analysis where we select the best potential parents for the future generations. And this is where we estimate the breeding values. And I've seen through my experience a lot of different ranges of types of analysis with drawbacks, with some difficulties, simplifications, and so on. So let me just start why we want to really do breeding value estimation. We want to select the individuals that will be the parents for our next generation. This is pretty much like an animal breeding or animal model. If you think about it, we have a breeding value for all the parents, for all the grandparents, for all the kids, and we want to select the best potential parent to constitute the next generation. And obviously, we want to use all the available information we have in our breeding program, which can span for several years. And obviously, this is not very easy. And this is what I call the big BLUP, because every once in a while, not necessarily every year, but every once in a while, particularly in trees, we have a bit longer cycles. We decide to pull all the data we have historically, maybe the last 10 years, the last 15 years, from different types of designs, and we want to do a full analysis where we obviously have some pedigree information or some genomics data, and we do this big BLUP. So it makes sense to combine all the information. I don't want to use just the data from the last season or the last year, because yes, I do have some pedigree, I have some information about relatives, but in reality, I'm only using, for example, the last generation when I have historical information of 2, 3, or 4 generations behind, and sometimes with different types of tests. So I want to make use of all that information with all the issues of unbalance, missingness, different types of design into a big BLUP analysis. And again, I have here a little bit of a figure on the side that really what it does is it just shows us that as we select different individuals to constitute the next generation, what we're doing is we're shifting the distribution into a recurrent selection program or whichever sort of program you have, and then we are moving that distribution of the individuals. So I'm selecting potentially the best one, but my idea is to make that improvement of my base population for all the traits. We also do this analysis not only to get the breeding values and make the selections. Breeding values could also be twice the GCA. We also obtain some parameters, some particularly variance components that are relevant. We get an idea of the heritability, and I'm biased because it's a heritability across all the trials that we're doing this analysis. We can also get heritabilities by trial. We assess the type B correlation, or what is the level of G by E we have, and it probably is going to go all over the place because we have trials better connected in different conditions and so on. But in general, we look at what is the main range, what is the main values that we have, and so on. And you can see here in the drawing a little bit of a structure with some clustering. And obviously, the other thing is with all those bits of information, it allows me to make better decisions on defining a strategy and what I'm going to do with this. Obviously, besides the selection of the best parents, but you might identify, for example, there's groups of the population that seem promising, but they haven't been used. For example, some all grandparents, or that you have a clear clustering of your sites that defines that maybe you need to focus a bit more in some areas or less in some areas, or they have a lot of G by E and you have to change some things and so on. So defining the strategy or looking a bit at some of this is relevant. Now, that's an ideal situation. Sometimes we cannot get all those, like for example, a correlation between every pair of sites. We have to use something simplified models, which I'll show you, maybe with a common correlation, some simplification of the model terms and so on, which is still is useful to make those decisions and so on. So one of the things when this big BLUP, and I'm thinking about, okay, let's pull the data from the last 10 years from my breeding program. I have lots of different experimental designs. And this is where the complexity comes. Experimental designs that are p-reps and replicated. They are even part of a split plot design, row column designs, incomplete block designs with checks, with changing checks, different generations, with different subpopulations and so on. So obviously there is going to be a lot of complexity there, and then you have to make a good decision on what you're going to use for this big BLUP analysis. And it doesn't have to be fixed, but obviously you want to simplify your life. And you have to change a little bit the way you think about this. Is you're not thinking about, oh, this is the variety that is being tested on these 3 types of tests. It's about these are the parents that have been tested, or these are the subpopulations that have been tested. So you shift your vision from that individual genotype to a parent or to a family that has been evaluated, and particularly a parent that has been used maybe on several crosses over the last 3 or 4 years, that where you now know it has good connection between trials, it's being tested with several other parents, and so on. So that's one way to decide what you're going to consider. And obviously you have multiple stages, and this is just one example from one reference where you have stages with different number of crosses or families and individuals tested by a pre-selection of families, and you see how the numbers go down on the terms of number of plants or entries in this case. And probably here you want to decide that all up to certain level, because you have different stages and different levels of selection, you're going to stop there. So for example, less than 50 genotypes, you're going to say, no, I'm not going to use those trials. I'm going to use all the other information. But the beauty of it is that you might have the same, say, family that is being tested with different individuals and maybe even some of the same selections over time. So that means you have a good representation across the stages, across years, seasons, and that allows you to estimate a little bit better this GBLUP. Again, I'm considering that this is parents that are being tested on different places. Now, each trial will have its own personality, which is going to bring a problem. So there's quite a lot of work to do ahead. You need to clean for outliers. You need to look for special trends. You need to have the correct experimental design with the correct definition of the model. And also the other thing that happens is that some things are going to change over time. And this also defines how complex you want to make it. Are you going to subdivide it into subpopulations? I remember I was working in one case where some of the practices changed, like in 2006. They changed the way they produced the plants. So that means anything before 2006 was kind of like different conditions. So we decided to drop all of that, and we only took out the information beyond that year. Obviously, we have things as global warming and strategies and merging of companies and so on that also defines where do we want to stop or what is the data we want to combine. Okay. And obviously, this is going to come with lots of difficulties. So you can already guess, I'm going to pull all these trials together. I'm going to have all of them need to be in the same common database. They are going to have their own issues. You need quite a lot of prior checks, exploratory data analysis, some of the recoding, and this is very important. The names of some of the genotypes change. The pedigrees need to be assessed. The factors, sometimes they have inconsistent names, sometimes because they come from different countries or because the designs have been done in different ways. And one of the things, again, with this paradigm of looking at the parents, at the level of the parents, you need to assess for connectivity. And I keep emphasizing this, but a parent that is only being tested on one trial, only with one another parent, is going to be independent and is going to be as isolated in one of the environments. So it will be very difficult to link it to the other individuals. It'll be very difficult to assess a good and have a good estimation of GBLUP. So what we look here is for good connections, parents represented on different years, ideally in different crosses. There's going to be a shift, and there's going to be a group of trials that have nothing to do with the other trials because there's been a shift on the generations. We also have genomics data, which will help me to connect. But sometimes the new generation has to do with the older generation, and then we'll have some relatedness through the genomics data. Sometimes we only have the pedigree, which is fine. But this is very important because there was a few cases, for example, where a company buys another company and the two breeding programs kind of merge, but they have nothing in common. They started with different populations, and that means they are not going to be good historical connectivity, just the present connectivity. And of course, you're going to try to fit different variance components, incomplete block variance components, spatial variance components, and so on to all of these things. So there's going to be a difficulty on trying to get all the data at once. And sometimes that means you need to make shortcuts and have some simplifications on what you need to do. Okay, so just one sec. Okay. So those are things that are important. Yeah. So, but there is a lot of planning. And once you do some of these analysis, which is something I haven't mentioned too much, is when you start doing these types of analysis, you realize what the problems your data have. And those are things that you take home to improve for obviously the next round of things, how things get better connected or better assessed. For example, the typical case is that you have one parent cross with one other parent in a single cross only tested on one season or on one, and that creates a little bit of confounding of the dominance, a little bit of confounding of the GBLUP. So you kind of say, okay, well, I need to at least use it in two crosses or at least test it on 2 different years and so on. Okay. Now, nothing is going to be perfect. This is obviously going through historical data. And one of the things, and this again going back a little bit to the forestry data, I want to use all relevant information I have, the historical information from the last 10, 15 years. So I have pedigree. And this is one of the things. I have pedigree, I have phenotypic data, and recently I might have some genotypic data. And this brings putting all them together into a same unique analysis with all the complexities that I have mentioned. So I am a big defender of using the pedigree. In forestry, it's very important because on some of the perennials, like cocoa and coffee, and even banana and some other crops, because you don't have genotypic data for the last 15 years. You only have phenotypic, you don't have genotypic data for the last 15, 20 years. Those individuals are dead. You only have a group of genotypic data at the present. You don't want to discard that information because that information has been very valuable on those times to make the selection, pre-genomics. And then obviously that information with the phenotypic information and all that is the evaluation of the parents of the current generation. So for that reason, you say, well, I'm going to try to recover and use as much as I can from that historical data. And that also implies bringing out the pedigree to today. And that brings especially other challenges because once we have pedigree and genotyping information, we need to communicate properly. And this is why we talk about the single-step GBLUP, or sometimes we have the HBLUP, where we are able to combine all this. In some breeding programs, you have no genotyping information, and that's also okay. That still brings a tremendous value of combining all that information. But often what it happens is this challenge of bringing these three sources of information. Maybe you even have a fourth one if you're using some omics or some environmental data and so on. Okay. So that's a little bit of what is happening with all of this information. Now let me show you a little bit of the workflow, and this is the way I normally process all this information. Again, it's not easy. It takes a little bit of planning. I haven't talked about, first we have to prepare the phenotypic data, we have to prepare the pedigree, and we have to prepare the genotypic data. And assuming that is all okay, I'm thinking of preparing it individually. So obviously the preparation of the phenotypic data is cleaning data, making sure the factors are well defined, they're standardized, etc. And then the pedigree, I'll talk a little bit more about the pedigree and the genomics data, but I have other talks where I have mentioned that too. So the single site analysis, one of the challenges sometimes is define what is your site. So in many normal traditional breeding programs in forestry, it's very clear that we have a couple of trials that are set up every year. Now, some of these trials might be clones. Some of these trials might be open families. Some of the trials will be just at the level of families. There's a different thing. So we have to assess what information there is. I've been in other breeding programs where actually it's a bit difficult to define what is the unit for the single site analysis because sometimes the trials are all planted together. And there are connections, but sometimes the connections are not very good. So you have to define what is the unit that I tend to call it like your trial unit or your test unit. And that is a unit on which one we are going to assess individually. Okay, so we analyze each of these units or sites individually. And then obviously you need to define the design effects. You put the proper design effects. You have to find the proper spatial components and so on, define all the factors and the terms that are associated with experimental design. In forestry, it's particularly relevant to have the plots. When you have measurements within plots, and some trials don't have plots, you have incomplete blocks, you have whatever structure that you will define. And then I'm again a big defender of doing some form of a spatial analysis if you have the coordinates. Now, autoregressive or splines or something. You can also use some simple, more simpler spatial analysis with the splines is one of them, but sometimes just to have rows and rep within columns and so on. But you will fit several spatial analysis. So this is on itself, it's just kind of like a cranking loop that tests several models and defines which one is the model that you select to be the best one for that data. And those are models that you're going to kind of like keep to yourself because those are the models that you're going to bring later on. There might be factors that are not significant. There might be outliers that you need to eliminate, and then you calculate heritabilities. Everything that you do on this stage helps to avoid issues on the big BLUP analysis that you're going to do later, okay? So there's a few questions. I'll come back to those questions a little bit later, okay? Now, this analysis usually is heritability, depending on your trial, could be at the broad sense heritability, and that's a good measure, or it could be if you have some pedigree already prepared or the genomics prepared, you calculate the heritability at the level of the, in this case, narrow sense heritability. Both are good measures. It's almost like a statistics to tell you if the models are adequate or not, okay? Now, this takes a lot of time. And then depending on, I haven't mentioned this, but depending on the strategies you pick, if you want to do a one-stage approach, which means you're going to put everything in one model and you're going to fit all the variance components at once, which sometimes is possible. It takes a little bit more energy. You only store some of the variance components as initial estimates. If you decide to go to a two-stage approach, which means you first get the predictions as blues, so as fixed effects on your genotypes with the corresponding weights, and then you take that information into a two-stage, that's also very possible. It changes a little bit of the way you do things, because once you do the predictions, you don't worry more about the design or what are the characteristics of the design. You just make sure you bring up the weights. And in general, that's an approach I try to use too, especially when there is a lot of messiness on the experiments, okay? So, but again, I'm sure most of you have done single site analysis and so on, and then the idea is just to crank the site and make sure you're happy with it, and then it gives you some statistics that you will use. When you go into the multiple site analysis, I go back to some of the statistics that I retain, particularly the heritability. Is a heritability that is too low, it means the site has to be eliminated. Now you have to think about the range of heritabilities you find, but a heritability that is, let's say, 0.1, where the majority is 0.4, it tells you there's something wrong with that site, you probably want to eliminate it, okay? Now this assessment is done by traits. So the different traits might have slightly different trials that get selected for their big BLUP analysis. On top of that, you look also some phenotypic data. So if you're looking at some incidence of a disease, if the incidence of the disease is too low, probably the heritability is also going to be too low, but then that means I don't have much information in there for that trait. And that eliminates some of those elements. Okay. So there is a couple of questions. I'll answer a couple of the questions. My recommendation for good connectivity between environments, if I'm thinking at the level of the parents, sometimes you don't have to worry too much about it because of the genomics data. But if you're using only Pedigree, you probably want, I will say, at least 10 parents in common. This is just, it's very difficult to assess what is the good number, but if you think about estimating a correlation between two environments and they have only 10 parents in common, that means they have 10 points in common. Okay, so it's a correlation that is best estimated with those 10 points. But because you're dealing with a bunch of different sites, some of the sites have very poor connectivity, probably no, and some of the sites will have very strong connectivity. So you have to assess this a little bit. Somebody's asking, when working with pedigrees, things can get messy, especially with complex extractors like different generation crosses, back crosses, and other mating. In your experience, how many generations back is actually worth tracing? And at what point is useful or is not useful? If I'm going on the generation you are focusing, you only need probably no more than 3 generations backwards for pedigree, but sometimes you are focused on selecting the parents, which means you're focused on selecting the parents from the previous generation or maybe grandparents. So I will say more than 3 generations from the one of your target generations for predictions. I will say that's enough. But if you're wanting to track inbreeding and you want to have a good match with the genomics data, it's likely that you want to have to take more generations backwards. Okay. And the final question is, what do you mean when mention the plot as a random effect? Well, for me, some of the stratum levels are random effects. Plot is one of them to avoid pseudo replication. So you will have plot as a random effect. Incomplete block is another one that tends to be as a random effect. I should be as a random effect. But the rep, when it's all orthogonal to everything else, could be either. So that's good. Okay. Okay. So when I do this multiple site analysis, it goes back to the process of selecting what am I going to use for this trait to analyze the data, okay? And you already have some idea of trials that need to be left out because garbage in doesn't really contribute too much. There is other decisions about, I mentioned about the incidence levels and so on. And the other thing is about sometimes there's a few tricks. In forestry, some people like to do the data standardization. And this goes with things like you might have different ages. In forestry, sometimes you have trials that are 3 years old and 13 years old with completely different scales. So there needs to be some sort of a standardization on it. For other studies also, it is done when you have very different yields and so on. I'm not going to go too much into that detail, but there is something common. And actually the data I'm using in eucalyptus has been kind of re-standardized to make them equally. It has some statistical benefits like reducing some of the variance components to estimate. One of the problems is that your breeding values now are probably in standard deviations or in relation to a reference that you use as a standardization reference. But it is quite common, and in animal breeding, you see it a lot too. Now you're going to combine everything into a simple analysis. And the best way is to start with something very simple. I like the interaction model, which is genotype and genotype by environment, maybe with heterogeneous errors, but with all the other variance components that come. And you will see additional outliers, and you will see additional problems and elements that are not significant and maybe they were before significant. So you have to kind of go back and reclean the data and reclean your model. And then you would progress slowly to more modern models if you can. So you can go to, if you're familiar with a core H or core GH or factor analytic, but some of them you will not be able to fit, like a core GH with hundreds of trials, it won't be. But core H, which is a single correlation heterogeneous variances, is one of the models I like to use for this big BLUP analysis, okay? Now you fit different models, have to define once more statistics to say which one is the best model. And then every time you fit a model, you say, does it make sense? The heritabilities are okay. Do I have error variances that are too small or too large? What is happening here? Is the level of correlations reasonable? And you look at some of the breeding values too, and so on, to assess that everything is okay. This is because there's a lot of confounding, okay? And you have to make a bit of a decision there, what happens, okay? So all this is, a BigBLUP is focused in an animal model. I have just this slide to remind you that I'm really going to fit a model with an individual and probably individual interacting with environment, but I'm going to use or a pedigree based analysis or PBLUP, or I'm going to use a genomic based analysis with GBLUP, or the combination of both of them. So pedigree, let me just go back a little bit to the pedigree. I think it's extremely important. In forestry, we have data for the last 30 years because the generations take 7 to 9 years. So I only have 3 generations backwards besides the current one. And it's very valuable information, but it needs to be maintained. And obviously, if we have genotypic information and you're going to have genotypic information that you want to combine, you want a good agreement between your pedigree and your genomics data, and try to identify where it might be the issue if there's not an issue. So cleaning the pedigree, preparing the pedigree, proper management of the pedigree. When you set up a new experiment, define a unique ID for each of the new individuals and keeping track of that. It's super, super important if your goal is to keep doing this BigBLUP analysis, and things just get more complicated, okay? If you are building the pedigree for the first time, that's fine. It's a good investment. I think it's a good investment. And then you have obviously decide how far back you want to go into this, okay? So that's one of the things. That's it. And then obviously define everything on the pedigree and so on, and check some things on the pedigree, how sparse it is and so on. And then we get the genomic matrix, and you've seen some of my slides before in other talks. So genomic matrix, we take the genomics, we prepare it, we calculate the GRM or the G matrix based on molecular markers, based on band rating. There's all this process of cleaning, preparing data and so on, and also some manipulations to make it stable and make it invertible, okay? So I'm not talking too much about it, but one of the things that is important is that this genomic matrix helps me to check the pedigree and vice versa. Okay, because my goal is to combine them all together. And then we use the single-step GBLUP. The single-step GBLUP, on the sense that I'm building the H matrix or the H inverse, with the goal of replacing a portion of the G matrix, of the portion of the A matrix by a G matrix. And then obviously there's these funny operations in between here, which what they do is they update the parents and the grandparents and the other individuals that have not been genotyped in relationship to their relationship to those individuals in there. So this is extremely powerful. You have other tricks with coefficients that you can add to say how much portion of one or the other you are adding in there and so on. And then you also require some checking to see if it makes sense, okay? But if you trust your A and you have used your A before, then you will trust your H most of the time, okay? So, a couple of questions. If we focus on unreplicating trials, can we proceed directly to multi-site analysis for data assessment and outlier elimination? Yes and no. It is probably good to assess if there are outliers on the unreplicated trials, and you'll find some things. And heritability also will be reflected there, even that it's more difficult because your heritability is mostly estimated from untested trials. But what you can do is you can go to the higher level, which is the series of trials. So you have unreplicated trials, which is 5 trials that were put together. Maybe you just analyze those 5, and from there you make a whole decision, but you need to make it flexible enough before you go to the BigBLUP. So maybe you want to do unreplicated trials analysis by season, and then once you clean every season, then you combine them together into a BigBLUP. Somebody's asking, talking about generation weights using 2-stage approach is a good sign to have weights greater than the LS means. I don't know about that, so I'll have to come back to you with that because I'm not sure. I'm not sure. Besides LS means, we don't use LS means, we use REML means or predictions. So I'm not sure about that. And then the last question is how to fit the single stage analysis in case you have different experimental design from one another trial. So I will use a lot of that command for that question. I'll use the add statement and I'll define some more things later on. Okay. So now let me just go to the data to show you something. I don't have much time, so but and I'm trying to bring a lot of different things. This is an eucalyptus data set. It's particularly two trials. They are both randomized complete block designs. But one of the trials is for has plots of 4 trees and 6 replicates with 229 families. They're OP, open pollinated families, so we only know one of the parent, the female parent. We don't know the male parent. And the other side is single tree plots with 30 replicates per family and 244 families. Not all the families are common between themselves. There is an overlap of the families, which means there's an overlap of the parents, which is nice, good connection there. But some of the families are not represented on both sides, and that's very common, okay? We have different traits, mostly yield, survival. There's something about wood quality. And the pedigree is only 2 generations. So it's a relatively poor pedigree because we have the parents and we have the kids and nothing else. But if I have more information, I will add the relationship of the parents or genotype the parents. And we have the genotypic data of a sample of individuals. So only 8 trees per family per site. Okay, so there is a lot of trees per family on these studies, but only a subsample of them were selected to be genotyped. So in this case, only a group of families and only a group of the individuals per family. So the same goes for both trials. So only 423 trees out of the close to 2,000 trees were genotyped. So that means we need to use the pedigree, and the SNP data is only 2,000 SNPs, which is okay. It gives reasonable results, but it's obviously not necessarily the best idea. Okay, so let me just go a little bit to the codes, and we have. Let me just have too many things open, and I can't see all the messages. Okay, so hopefully you can see that screen well. Just going a little bit bigger. So I'm going to read the data. I'm just going to go a little bit quickly and we can make this code available. Just reading the marker data, which is already imputed and so on. And then I do the typical cleaning of the marker information. So some level of missingness, some level of heterogeneity, if there are some values to be imputed or not. And obviously this is just a simple preparation and there's no many marks that were dropped. We end up with a little less than 2,000. And obviously we can explore the matrices and so on. So I have a few statistics and tables that we use to assess if we're happy with the marker data or not, missing data and so on. So everything is imputed, so these are all fine. I'm not going to spend too much time on this. I save the matrix because I might want to use it for something else. And we also calculate the genomic matrix, and we can do some assessments of the genomic matrix. And you can see the values on the diagonal are higher than 1, which is a bit of a surprise in this, and this denotes some issues. And the values of the off-diagonal go all the way to 154. So this is where we might want to say, oh, do we have issues? Do we have to eliminate some things? Again, I'm just looking at the molecular matrix. I'm not surprised with these results given the low level of individuals, the low level of markers, and not so many individuals genotype. And then eventually we do some blending and preparation of the matrix, and we recheck the matrix. The blending means I average it with an identity with 5% on identity, and so on. So it is just making a little bit more of the preparation. And then here you have the values on the diagonal, which are surprised. They're all a little bit of inbreeding. Is that reasonable? Is because the parents were inbred, or is because the kids were collected the seeds from the same place where they was open pollinated, but actually an eucalyptus have some level of inbreeding too. We need to check if that makes sense. And this is the off-diagonal value center at 0 with some half sieves, full sieves, and some individuals that seem to be duplicates and so on, which is a little bit concerning. But anyway, we obtain our inverse, we save the inverse, and we can do something similar with the pedigree, and we can get the A matrix for the pedigree. And what I'm doing here in another function, and again, I'm just going to mention this is a bit quickly, but I did save all of this. After I am happy with my genomic matrix, I go to my pedigree matrix and also make sure it is reasonable or not reasonable. And this is just constructing on the background because it's a relatively large pedigree. It's actually 10,000 trees. And we have a difference between some of the individuals. These are a sample of the individuals from the genomic matrix and so on. Things you need to consider here is that you need to match the GRM to the A matrix. So find individuals that are common. And then some people use alignment, and you might want to match them a little bit. Let me just show you the two different matrices, which I like to use for some checking. Individuals are declared half-sieve here, and everybody else is declared, and then everybody else kind of declare independent. And you can see here the relationship between that half-sieve is actually 0. So it's not being declared as a half-sieve, probably pollen contamination or something going on. Okay. Again, all these checks are kind of important to assess how well the A and the G are going to talk each other once you do the H matrix. And you can see here from this plot that it is a bit bizarre because there's relationship declares to be half-sieve that go all the way from -0 to all the way to almost 1 or even higher than 1. So there's probably some issues here on the pedigree or on the genomics and so on, okay? I'm not going to go more into details, but I managed to get the H matrix. And the H matrix gives me some interesting relationships. I think I can use this. It might take a little bit of time. It's kind of stupid of me. But you can calculate the H matrix, and I saved it. Or you can calculate the, or the H inverse. And I just want to show you a little bit of difference between the A and the H matrix. So it looks okay. There are some relationships that are being declared on the parents. These parents that were not genotyped, that the relationships are being declared because the kids are related. And also, when you look at another group of individuals that are independent to each other, which is offsprings, and you can see again some weak relationships between themselves, which is what I would expect. Okay, now once more, I'm a bit surprised that the values in the diagonal are all consistently lower than 1 in this particular set. So anyway, so I'm assuming I already prepared my H matrix, I already checked my pedigree, and now I'm ready to do my analysis with my data set, okay? So the first thing is I have this eucalyptus data set, okay? It is only 2 sites, Dong Meng and Jun Ling or something like that. We have different factors of rep. We have plots defined. Sometimes we have a row defined, sometimes we don't. Tree number of 3 within the plot, families and the female and the male part of the pedigree, and some response variables. I'm going to focus mostly on height. And this is adjusted height because I am saying that they were standardized. But one of the trials has plot effect, the other trial doesn't have plot effect. One of the trials have row effect, which we can use to control for some spatial variability. And this is where we might have several trials with different elements defined, incomplete blocks. I don't have an incomplete block here, but I might have them. In other cases, you might have row and column designs. So that means you have a row effect and a column effect, and then you need to kind of or do an spatial, or you want to put the row effect as a random effect for within rep or within column, all those elements that you might have, okay? So that's where things get a bit messy and you need to prepare everything properly. I need to emphasize that the names of the individuals and the names of the females and males have to be very consistently checked because of changes of name, because sometimes you have an underscore that somebody used years ago, because or the name of the genotypes have changed once you use them as a parent, change the name. And then so all of those things, you need to be very, very careful how they are set up, okay? Also, obviously, things about how you treat the missing values, what its lower limit for each of these traits. So can I have a negative value for one of these? Does it make sense? Or can I have a 0 value, etc. So this is where everything becomes a bit more messy. So I'm going to define my factors. Everything I can think of might be relevant. And again, just some exploratory data analysis. The combination of DVH for all the sites. And these are DVH for the different ones. Actually, I'm working with height. So I can look at height, and then you can see some extremes here and there. Again, because things are being standardized here, the ranges are similar and the means are very similar, okay? So now I read my pedigree. Why do I read my pedigree? Because my focus is on getting the A inverse, which I'm calling it A inverse sparse, to do an analysis with the A inverse. Now I have also the H inverse. So I'm just going to show you a little bit of the difference, kind of like for my peace of mind to make sure everything works okay. Now, sometimes you only have the A, fine. And sometimes you can't bring in the genomics, that's fine. Or sometimes you just use directly the H inverse and the computationals are there, okay? So I got the A inverse directly to be read by ASReml. And in this case, what I'm doing is I'm reading the actual H inverse that I prepared before, and I'm going to select one of the levels, which is the first site. So this is where I go to analyze each of the sites individually. And you respect some checking, like I'm just have how many individuals, how many observations per rep per family do I have? And then, this is the plot and so on. And then other things about, do I have row terms and so on. And again, this is to understand how the site one is happening. But here is where you have all the options. You say, okay, this one has a plot effect. This is based on the A inverse. And then I commented this out because this one doesn't have this term, but the second trial has that term. You might want to add autoregressive components. You might want to add splines if you have the rows and the columns. You might test it in different ways. At the end, you define a model that you're happy with it that describes the data for that particular site. With that on mind, you fit the model, check for outliers. You can be more flexible or more strict. And this case seems to be potentially something on the bottom. Again, depends on how much data you have per site, so on. You want to eliminate them early so they are not showing up later on the potential error analysis, and a big outlier will inflate correlations either way, okay? Some of the variance components, which tells me I have a plot effect that is significant, and I have a heritability that I can calculate, and I store that, okay? So, and then maybe with other summary statistics, and I move on to the other trial. Now I put a couple of comments here. You might want to expand your analysis with other spatial components. You might want to add the family term. If you're dealing with clones, you might add a clone effect. So like the non-additive term in your model, you have to assess if it looks reasonable or not, but you might want to add it, and many other things. So sometimes I put the SCA, like family term, sometimes the clone term. So you assess the model for that site the best you can, okay? So somebody says, because trees in the same plot belong to the same family, isn't the plot variance confounded with the family variance? No, it's not, because you have several trees per several reps. So the family is represented on every rep. So it doesn't happen. When you have only one rep on only one family, yes, the plot, only one plot per family across the whole study, then it gets confounded. Okay. Anyway, let me show you the second trial. The second trial, the logic is the same, but now it has a different term, rep row, and it doesn't have the plot term because these are single tree plots. So the calculations are a bit different. The plot will be obviously a bit different. And then once more, you eliminate outliers. And the heritability in this case is higher, 0.66. Okay. So anyway, once you are happy with this, you decide to go on and combine them all into a single analysis. But here is where it's important that where you just did the analysis and revisit your selection of trials to analyze them. And one of the things that you check is also the connectivity. So first I make a selection, which trials are in, which are out, or because of heritabilities, because of problem, because of populations or incidence of diseases. And I'm using ASR trial to give me something about the incidence, so it means how well connected these are. Now, this is done by family. You can do it by parent, you can do it by clone, but notice that I have 227 families on this one, 244 on this one, 216 are in common. This is only 2 sites. If I had 26 sites or 150 sites, you have this giantous matrix, and you can see there how well connected it is, and maybe you can even identify clusters. And you might eventually identify sections that are completely disconnected from each other, which brings a bit of a problem to decide if you have to split it or not. Okay. And this is where it comes to build my models. And I have just a couple of slides here. I like to focus on 2 models, the interaction model and the nested model for G by E. The interaction model is where you have a main effect of genotype. Notice that here I have yield, site, genotype, and genotype by site with heterogeneous errors for the residual part. So I have these associated with an H inverse for genotype, and I have the interaction genotype by environment. This is a very good model, will always fit, but it has the problem that, and I mentioned this before, that assumes the same correlation across any pairs of sites and a common genetic variance across all the sites, which sometimes is not correct. If you have standardized things, it's more likely to be correct, but sometimes it's not correct. But this model will always fit, and it will give you a reasonable breeding value of the genotype across all the sites, or will give you G by E's on those sites where that genotype is present directly or indirectly. Okay, so this is, you can then rank the genotypes and it's fine. Okay, I like to use heterogeneous residuals because every environment has different levels of heritability. Again, depends if you standardize or not. Now, I think this is a more appropriate model. It's where you have the nested effect. So you have only genotype nested within site. So you can use a core GH. If you can, probably you won't be able to fit it, but you can use a core H, which is a simple model with a common correlation between every pairs of site, but heterogeneous variances for each of the sites. Together with the heterogeneous error variances, allows each site to weigh differently when you calculate the breeding values. Okay, so if an individual is only tested on some of the bad sites, it's going to have breeding values close to 0. If an individual is tested on good sites, it's going to have a relatively reasonable breeding value. Okay, and so on, and you respect also the different scales. So this model is better, and if you cannot fit the core GH, you can fit the core H, which is very reasonable still. It doesn't give you too much of those correlations, or you can try some of the factor analytic models with order 1, 2, 3, 4, whatever the ASReml can fit relatively nicely, and it gives you an approximation to this more complex correlation, and that can give you better information. Okay, so this is what I'm going to do here. Now, this is only 2 sites, but I could have a lot more terms, and I have had models like this with 50 sites, where lots of different terms per site and so on. There's a couple of key elements. The main element is the use of this at. I'm saying for site number 1, level 1, please give me a plot effect. For the site number 2 or level 2 of that site, please give me a row within rep effect. And you can have multiple of these. For at site 16, give me incomplete blocks. At site 19, give me a splines. And each of the sites will have their own specific terms. And also, once you go to some of the genetic terms, you say for at site 19, give me a family ID, because I have SCA and the other ones I don't have, or a non-additive effect. It gets more complicated to fit, but it does bring whatever bits you need from each of those models. And at the end, you have this genotype using the A inverse, or genotype using the interaction with site. Okay, I'm using a very simple one. You fit this model. In this case, it's not much data. Again, you can assess the residual plots by site and find additional outliers, or you focus on the variance components and can calculate, for example, in this case, I'm calculating a type A correlation, which should be type B. So this is 0.49 is the correlation between the breeding values on one side against the other side. Now here I'm using the A inverse. On the second model is, I'm still using the A inverse, but I changed from an interaction model to a nested model using a core GH. And when you look at the residual plots for the look at the log likelihood, it's 98, 95, which is a little bit better than the previous one. It was 98, 98. 3 points a bit better. And the variance components are describing a correlation between the two sites, which is very similar to the previous one. And then also different variances that are very similar because of the standardization. Something similar happens with the error variances too. So some of the things are, well, no, this one don't have to be similar. These ones are not that similar and these are not that similar, so which is good. Okay, I can calculate goodness of fit to assess which one of the models is a bit better. Log likelihood is one. In this case, the models are not nested, but they could be made nested with a core V. Or I use AIC and BIC, which again tells me that the second model is a little bit better. Okay, so this is where you play with different models, add different bets, and so on. Okay. Now I'm going to use the A inverse, like the H inverse instead of the A inverse, because I did all that work. So now everything is more connected, you know, and these models tend, because you're using the genomics and everything is more connected in one sense through the relationships, it tends to give a little bit more stability and so on. And at the end of the day, what you get is, this is called MET, which is the previous one. And the log likelihood of this model, which is using a different genomic matrix, it's a little bit better than before, which is great. That's what I was expecting. Sometimes it's not, but often it is. And the variance components change a little bit, but not excessively. You have 0.45 here, sorry, yeah, 0.45 compared to what we have of 0.436. Okay, still quite a bit of G by E in this particular case. And then you can calculate heritabilities and kind of start wrapping up your results. Okay, you can calculate based on this analysis heritability by site, or you can calculate an overall heritability, which in this case is 0.53. Just briefly, I'm just going to show you that you get the GLAP values, which are the breeding values of each of the individuals, kids and parents. Everybody who's defined on the pedigree has a breeding value. And I can, in this case, I'm having the individuals, oh, sorry, let me just show you again that. You have each individual being defined. So this is individual number 1, which is one of the grandparents or parents, on both of the sites with a breeding value by site. Remember, the correlation is 0.49, which means there's quite a lot of change on rankings between the two sites. But again, you can select the best individual with the breeding value 0.761 and so on. And yes, so it gives you a few of these individuals. I wouldn't be surprised they belong to the same parent. And you can make your selection. Okay, so just a couple of slides. I'm going almost over it, but again, this was just a textbook example because it's 2 sites. But if we have a lot of sites, I will have a breeding value for each of the sites. I will have more statements to describe each of the sites. And I end up with a breeding value for each individual in each site. And then I can average the breeding value across the site to get the overall performance of that individual across everything. And that is my big BLUP that I can use to make rankings and selection. You can also assess the breeding values and see if some sites are more grouped than others and so on. Okay, sorry. So a couple of last words. I'm usually plan to do this for an analysis for a company, but maybe a couple of years later, I'll come back to redo it again. So all the preparation and all the things that come up are really important. It still will be hard to combine all the pieces into a single system today or tomorrow, so you have to do it. Every data source has to be prepared and cleaned, hopefully today, so there it is nice to update in the future. And that means the phenotypic data, the pedigree, and the genotyping, and everything you do to make this a bit more smooth will make your big BLUP analysis later more smooth. This is without counting changes on the way you do testing on the future to make your big BLUP a bit easier to implement. And also, yeah, you get ready for how will you do this analysis in the future. Okay. Now you have other sources of information you might want to also use and incorporate. This environmics, other omics data, drone data, or indirect traits, and so on, which is probably going to be relevant. And again, it adds an extra complication, but it is possible. And you have to think that your information will grow and will grow and will grow. It's true that we add more information, but we decide to eliminate some of the older one because we are too far in terms of generations. But sometimes you don't. You just add, and then you have to make sure they all communicate well and they have reasonable structures on the data and they're well connected. Actually, you can adapt your crosses too. Okay. And things will change over time. So that means also you need to make sure you prepare for those things, maybe better designs, maybe the coordinates start to be more relevant. And also your platforms are going to change in terms of genomics. So you also have to kind of work on that end. Notice that I did something very different here. I prepared the whole genomic matrix with all the data I had before I decided how I was going to analyze this. And this often is a good practice unless you have millions of records, because it makes sure that genomics is stable and well prepared, and then you can always filter things out. Okay. So I'm going to stop here to leave a little bit of time for questions. And again, there's a few questions that I will answer. And I know I talk a little bit too much and we don't want to get too extended, but let's see. We have a couple of questions that I skipped before. Based on the range of all diagonal values, what do we detect the presence of each in the data set? Yes, the regular range of values on the diagonal is 0 to 2. Well, actually 1 to 2, a little bit less than 1 because of sampling on SNPs. And if there's no inbreeding, a little bit above 1. And if it's some inbreeding or even completely inbred lines, you expect something a little bit over 2. So sometimes it's an indication of problems. When it's 2 very negative, it tells you something is going on. Okay. So let's see, if you have a Pedigree account, you can proceed to STA or MTA. Otherwise, it's better to go straight to MTA. I don't know what STA is, multi-trait analysis. If you have a Pedigree, yeah, you can directly go to STA or MTA. So normally I prepare the full Pedigree and even the genomics, and I use them incorporating to do the single site analysis directly. So that shouldn't stop you from that, not just a subset of things you have. That's what I like to prepare everything before. Okay. And then the last question, it says, what do you don't have Pedigree and you're working with natural population, no crossing, it has been, well, I'm assuming you have genomics data. So then that will solve the problem. You don't worry about it. But if you don't have genomics data and then you are in a natural population, there's nothing that can connect multiple environments or families. So I'm not sure what will be done with the analysis. It is common also in some of the natural populations to genotype individuals at a low density panel and then reconstruct the pedigree and use the pedigree or a combination of the pedigree with the small density panel. Okay. How can you combine two different relationship structures, genomics plus phenomics? Oh, that's not very difficult. You can do things, well, just the dirty way is, for example, I'm not providing all the details, but you can have also a BM for site associated with an environmental inverse matrix, environmental covariables inverse matrix. You have to make sure you have a variance component associated to this one. So you have to create a vector of just once. And then that will create the variance associated with this. So there's a few tricks there, okay? How to estimate the heritability with the core GH model. You have, this is what I did here. Actually, I take the average of the genetic variances and then plus divided by the average of the genetic variances plus the average of the error variances. And when you have some terms that are present of absent, is the average of this 0.50 against 0. And then this 1.0. So there's different ways. It's not very straightforward. Good. And again, I know there's a lot of more questions. Anybody has a burning question? Do you want to mention it? Like, I will share the script. I know this was a bit quick.
Yeah, hand up from Max. Allow you to talk, Max, if you want to ask your question.
Mute. Oh, it was an accident. Okay, no worries.
Okay. Oh, there's one more from Kleber. Should we try that one?
Yeah. Oh, hello, Cleaver. You're also in mute. Or maybe it's another accident. We can't hear you. Maybe technical issues. You can bring the questions on the chat. I'll be answering some of these questions again. So yeah, so we'll be answering some of these bits, and I will make the data available also. So let's say Clever is here. I'd like to ask if the same approach you're using for prediction can also be applied to hybrid performance. Yes, it can be used for hybrid performance. Additionally, how can I leverage this method to predict the best parental lines for a combination between pools? Okay, so by hybrid performance, you have to think, I mean, if your objective is to select the best hybrids, that means you're not using the pedigree or the genomics. So the connectivity is more important. That's more like a traditional MET analysis. Now, if you want to predict or get a breeding value of the parents that form the hybrid, that means you need the pedigree of the parents or the genomics of the parents. And that means you need to bring the A inverse or the H inverse or the G inverse, whatever you have. So, and you can again, once more, get the performance of the parents as GCA and then sum them up to get a potential hybrid. And you can extend this to put some non-additive effects, which is mostly dominance or the SCA. If the data is good and you have the parents represented on several crosses, you can estimate the SCA for each of these and then try to improve the predictions of future crosses or current crosses and rank them. Okay? So it is possible. And then it says, how can I leverage this method to predict the best performance lines for the combination between pools? Well, there's a few tricks there for the pools. It has to be, I will have to understand a bit better how these pools were created, but sometimes you can estimate like breeding values of different subpopulations or forms of populations. So you create like a dummy pedigree, and then you can get a little bit of a better idea. Okay. So there is a couple more questions. May you please come back to the value of the G by E for the core GH model? So the G by E model, it is estimating this core GH, which means it's two variances and a correlation. So this is the correlation, and it says COR. This is the correlation between the BLUP effect across the two environments, 0.45. And this is the variance of the first environment domain and the variance of the second environment. If I had more environments, I will have a correlation for each pair of environments and a variance for each environment. And you can use that to make interpretations of your levels of G by E. This is only two sites. With 3, 4, or even 5 sites, you'll be okay using the core GH. Once you get to more complicated cases, so more than 5 sites, it starts becoming a bit unstable, and you tend to use other models like the factor analytic. So one asking, why do you need IDV when you're doing VM with VM? That's a good question. I need because the VM is not associated with any variance. It's just a correlation matrix, and you need a variance on top. Otherwise, ASReml will say, oh, you haven't specified a variance, or will assume the variance is 1. So, and this one is the same. This is a correlation matrix. All the VMs, the relationship matrices, or correlation matrix in this case for the environmental covariables, are correlation matrices. So they need a variance in the front to be well defined. And ASReml in some cases adds it automatically, like when you just put VM on itself. But when you do more, like in this case, it will add it automatically because it said, oh, you haven't defined one, I'll add one. But in some cases, it doesn't. So you just have to assist it, okay? Okay, well, then we have a thank. I don't want to get more extended. I know some of you have to go. But again, I want to thank you for joining us. This will be all the data is available if you want some more information. We also have the old webinars that have some details of why we do this and why we do that. Some of the slides have used them, but again, it should give you a bit more information. And thank you for all the questions and for joining us.